why we need Python for statistics. Well, we're all familiar with R. R is a language dedicated for statistics, right? So if that's the case, then why would we require Python for statistics again? Well, it's not just statistics, right? We're going to mix statistics with image analysis or text mining or any other complex pipeline as well. To do that, Python really helps us, and the richness of Python is definitely an invaluable asset here. And that would make our life so much easier, right? Well, if you were to ask for my opinion, if I had to start out with statistics again, I think I would definitely start out with Python and then probably consider R. Well, that's just personal preference. So moving on, let's check out what probability actually means. Well, at the most basic level, probability seeks to answer the question, what is the chance of an event happening, right? Well, look at it this way. An event is some outcome out of interest. To calculate the chance of an event happening, we need to also consider all the other events that can occur at that point of time as well, right? Well, to elaborate more on this, let's consider the coin toss problem, right? It's a classic problem for this purpose. Well, there are two events here, and these are considered to be the sample space. Well, what do we mean by sample space? It's basically all the outcomes for the coin toss. So when you toss a coin, there are only two chances and two occurrences, right? So it's basically either you get a heads or you get a tail. And if it's a fair coin, I don't think there can be any other possibility as well. So it's just heads or it's tails. So basically, these two form the sample space in our case. The set of all the possible events that can happen, right? So that's about it. To calculate the probability of an event occurring, we would have to count how many times the event of interest can occur. Say how many times you flip the coin and it landed on heads, or how many times you flip the coin and it landed on tails, right? And eventually we divide this total number by the sample space. So in our case, the sample space is only 2 because we only have a 1 in 2 chance, right? So it is either has to be heads or it has to be tails. Well, the probability will tell us that our ideal coin will have a 1 in 2 chance of being heads or tails. So that makes sense. So by looking at the events that can occur, the probability gives us like a framework, I would say, for making predictions about how the next events can occur as well. But not every case can be predicted correct, right? Well, consider this. You flip a coin 110 times. Out of those, you get 100 heads and 10 tails. Well, you might ask if this is fair. Well, it actually is. The outcome here is to basically gather the data, use the statistics, and make some predictions, and then eventually compare. Well, more on this in the next session, guys. So moving on, let's look at the data generation for our coin toss problem. Well, our data will be generated by flipping a coin 10 times and counting how many times we get heads, right? So let us say we will call a set of 10 coin tosses as a trial. So as soon as you flip 10 coins, there is not an ideal chance that 5 will be heads and 5 will be tails. But we do not need to worry about this since only one trial is our single data entry point in this particular case, right? So if we perform many trials, we can expect the average number of heads over all of these trials to approach to the 50%. And maybe we can consider then saying that it is either nearer to 50% or farther away from 50%. So now that here we have this image and I've explained the same thing as well, we need to convert this into code. Well, to do that, let's check out the code. Well, here the code is basically simulating 10, 100,000 and 100,000 trials, guys. And then we calculate the average proportions of how many heads that we actually observed. And here in the program, we have actually run a loop for 100 cases and then we're generating some data. So basically, the coin trail function is what represents a simulation of 10 coin tosses, right? And we're making use of the random function to generate a float value between 0 and 1. And later we'll increment our heads count to see if it is within half of our range obtained. Then lastly, simulate repeats these trials depending on how many times that you'd like, and it'll return an average number of heads across all the trials. So the coin toss simulations will give us some interesting results. Check out the results on the right side. Well, first, the data confirms that our average number of heads does approach what the probability suggests it should be, somewhere around 5, right? 50%. Well, yes. Furthermore, this average improves closer with the number of trials. As you can observe, we're at 5.4 when we simulate for 10 times, and eventually we come as close as 4.999, right? 4.999 when we simulate it 100,000 times. Well, in 10 trials, there is some error, but this error almost disappears when we do it with 100,000 trials, right? So as we get more trials, the deviation moves away from the average and the average decreases. Well, probability is basically putting a theory across and working on it later, while statistics is like basically testing those theories and drawing conclusions from them. So eventually the output we get is from our statistics, but the data gathered for the statistics is obtained by the probability, guys. So I hope I'm clear with that. So moving on, you may ask why you would require a proxy if you can just calculate just the theoretical probability itself, correct? Well, coin toss is a really simple example, but consider more interesting probabilities that are not very easily calculated, right? So what is the chance of someone developing a disease over time? How do you calculate this? And consider this other case as well. What is the probability that a critical car component will fail when you're driving? Well, there are no easy ways to calculate probabilities, so we must fall back on our data and the statistics to calculate them. Well, given more and more data, we can become more confident of what we actually calculate that represents the true probability of this important events happening, right? So moving on, we need to look at the data and how we can actually distribute the data. So basically, the question I have in mind for you guys is which wine is better than the other average, right? So this is another complex case. Well, before we tackle the question, we have to mind what is the nature of the data. Well, intuitively, we'd like to use the scores of the wine to compare it in groups, right? But there comes a problem. The scores usually fall in a range. So basically, wine is rated on a set of scores, and these scores usually fall in a range, right? So how do we compare groups of scores between the types of wines and later know with some degree of certainty that one is better than the other? So basically, how do we know that one is better than the other? Well, the normal distribution refers to a particularly important phenomenon in the realm of probability and statistics, guys. Well, the normal distribution looks exactly like this. The most important qualities you have to notice about the normal distribution is its symmetry and its shape. We've been calling it a distribution, but what exactly is being distributed here, right? Well, it depends on the context. So in a probability context, the high point in the normal distribution represents the event with the highest probability of occurrence, right? As you get farther away from this event on either side, the probability drops rapidly, forming that familiar bell shape as you can see on the graph. Well, the high point in a statistical content actually represents the mean. I'm sure many of us know what the mean is, right? So as in probability, you have to get farther away from the mean, you drop off rapidly from the frequency as well. And in our coin toss example, a single trial was used for 10 throws to produce a single estimate of what probably should happen, right? So we were expecting 5 heads and 5 tails at the same time. So we call this an estimate because we know that it won't be perfect. That is, we won't get 5 heads every time. So if we make many estimates, the center limit theorem dictates that the distribution of these estimates will look like the normal distribution. Well, guys, there is another rule as well. It's called as the 3 sigma rule. This 3 sigma rule dictates that given a normal distribution, 68% of your observations will fall between one standard deviation of the mean. 95% will fall within 2 and 99.7% will fall within 3. And next up, I have something called as a z-score for you guys. Well, the z-score is a simple calculation that answers the question. Well, what's the question you're wondering? Well, it's this. Well, let's say you're given a data point. How many standard deviations is it away from the mean? So we'll be calculating how far away it is based on the standard deviation here, right? And by itself, the z-score doesn't provide much information to you. It gains the most value when compared against the z-table, which tabulates the cumulative probability of a standard normal distribution as we discussed. Well, a standard normal is a normal distribution with a mean of 0 and a standard deviation of 1. Well, guys, this is something that you should remember. I'll repeat it again. Well, a standard normal is the normal distribution with a standard deviation of 1 and a mean of 0. And the z-score lets us reference this z-table even if our normal distribution is not standard, right? So even if our values are not matching the normal values, our z-score lets us to reference the table. And now I'm pretty sure you're wondering what cumulative probability is, right? Well, the cumulative probability is just the sum of the probabilities of all the values occurring up until one certain point. It doesn't have to be through all the cases at the same time, but we'll stop at one particular point. Well, an easy example to consider is probably the mean itself, right? So the mean is in the exact middle of the normal distribution. So we know that the sum of all the probabilities of getting the values from the left side up until the mean is 50%. So basically to reach the mean, you need to come 50%, right? And the values from the 3 sigma rules actually come up if you try to calculate the cumulative probability between these standard deviations. We'll consider the set of images. So in the first image on the left, we know that the sum of all the probabilities must be 100%. So that's true, like that's universally true. So we need to use the z-table to calculate probabilities on both sides using the z-score under the normal distribution as well. So we calculate the cumulative probability until a certain point and we call it z, right? So that's the z-score. And this calculation of probability of being past a certain z-score is useful to us. When so you're doing this, we'll stumble at this question. How far away is the value from the mean, or how likely is this value far from the mean to be used in the same group of observations, right? Well, the probability derived from the z-score and the z-table will answer all of these questions. So I'm pretty sure this has been a lot of theory, right? So enough with theory. Next up, I have this amazing use case that I believe that the majority of us can make use of. So basically, we'll be looking at if we can learn the concepts of probability by coding in Python. Well, let us consider this amazing use case of poker probability. Well, guys, can we predict the outcome of a probability of occurrence of a poker hand? So you might be wondering if you can actually predict this, right? I'm pretty sure this question is in many of our heads right now. And if you guys are poker players, I'm pretty sure you'll be wondering how as well. Well, actually, yes, we can do this. So let me walk you through a little bit of poker, right? So there are 52 cards in a standard deck of cards, and out of these 52, consider that there are 4 aces as well. Well, if you actually followed the example of coin flipping, then you'll know that the probability of drawing ace is actually dividing the total number of event outcomes by the sample space. So can you guys guess at this point what our actual event outcomes are and our sample space is? Well, let me answer that. Well, for our ace, since there are 4 aces and our sample space is of 52 cards, the outcome is actually 4 divided by 52. So let's start looking at some code, guys. Let me just quickly open up my Google Collaboratory and we can start working with the code. So here I've been connected to the kernel on my Google Collaboratory. So basically Google Collaboratory is just a Jupyter notebook hosted on one of their Google clouds, and it is amazing, guys. Well, without further ado, let's get started, right? So now let's determine the probability of drawing an ace with the help of Python. So guys, now let's determine the probability of drawing an ace with the help of Python, right? So we did it manually, so let's do it with Python. So we know that the number of faces is 4, the number of cards is 52. So our outcome is basically 4 by 52, right? So that is all we'll be printing here. And as soon as I run the code, we'll have the output to be 0.08. Well, to determine this probability in a percentage form, it's pretty simple. It's pretty obvious. We're going to multiply that with 100 and we're going to attach the percentage sign. Well, the probability of drawing an ace as a percent is 8% in total. And now that you've seen these two examples, these two tiny examples where you've calculated the probabilities, it is pretty easy to assume that you might build your own probability calculations, right? So let's say you want to determine the probability of drawing a card which is a heart or any face cards, right? Such as jacks, queens, or kings, or any combination of both, such as the queen of hearts, right? Well, in such cases, you might require a user-defined function. So in our case, we have a user-defined function and I've called it event probability. Well, this will help you to pass the event outcomes and the sample space to eventually find the probability of an event, right? So this will be in the percentage form, and we've actually used the function because we'll be reusing a lot of the code, right? So instead of typing out this code every time, all we have done is we have put it under a user defined function, guys. It's pretty much simple. So we've created the function that returns the probability percentage rounded to 1 decimal place, right? You can have any number, but I've rounded it here to be 1. We have the sample space to be 52 cards, and we have to determine the probability of drawing a heart. So we have 13 hearts, right? So what we're actually doing is we're dividing 13 by 25 and eventually converting that into percentage. So the probability of getting a heart is 25. And similarly, we have done it for the face card, which is 23.1%, and the queen of hearts, which is 1.9% as well. Well, I'm pretty sure these results don't surprise you. As expected, right? If you're a poker player, you know that the chance of drawing a queen of hearts are really smaller than the chance of drawing a regular card or a heart as well. So now that we have established that, we need to look a little bit into permutations and the basics of combinations as well. Well, instead of taking you through the theory of that, let's do it with code, right? So basically, we know that permutation is nothing but factorial n by factorial k. So yeah, let me go ahead and run the code. And as you can see, we obtained 12, right? So it is as straightforward as that. So next up, we have this code for combinations. Well, combinations will require permutations output as well to make it pretty much simpler. Well, so first, in this case, we'll require the factorial of n, and then we'll be dividing it by the factorial n minus k as well. And eventually, we'll be dividing this entire thing with factorial k. And this will give us the combination output for our case, right? So in our case, n is 52 and k is 2. So let me go ahead and run this and we'll get the output. Well, yeah, guys, as you can see, the output is 1326 for the combinations as well. Well, now that that's done, let's quickly go back to the presentation to talk a little bit on poker and consider two cases, all right? Well, before we get started, let me give you a quick heads up, right? So we need a little background info on this game called as Texas Hold'em. Well, it's played with a standard 52 card deck, and Texas Hold'em is one of the most popular of all of the poker variations. Well, there are multiple poker variations, and the Texas is definitely the most popular one, right? So here, each player is dealt with 2 cards to start with, and will make the best 5 card hand possible by using their 2 cards combined with 5 other community cards that are dealt throughout the hand, right? So cards are dealt in 4 rounds. First, we have the pre-flop where each player is dealt 2 cards and they're called as whole cards. And next we have the flop where 3 community cards are dealt, right? and turn, where here one of the community cards is dealt and revealed to the player. Lastly, we have something called as a river, where the final community card is dealt and revealed. So whenever I mean dealt, guys, it's basically revealing the card to the player. So consider this, guys. You're on your turn and you have 4 cards to an high ace flush, right? So basically a flush is a strong poker hand where all the 5 cards are in the same suit. Suit is basically the symbol, guys. So what's the probability that the last community card known as the river card is a diamond, right? So let's quickly go back to our code and let's see if Python can help us. So yeah, guys, back to collaboratory, right? So let's check out if actually Python can help us as I previously mentioned. So guys, we're back at the Google Collaboratory and let's determine the river flush probability as we previously discussed, right? So as soon as I go ahead and run this code, we'll have a probability of around 20%. Well, so that means that there is roughly a 20% chance of you hitting the flush draw on the river card. I mean the last card, right? So let's check out another case for a little bit of better clarity, right? So let's move back to the presentation quickly. So yeah, again, you're on your turn and you have an open-ended straight draw. Well, a straight is another strong hand where all the 5 cards are in a sequential order, right? So basically we're looking at numbers and not the symbols this time. The straight draw is open-ended because any 8, right? So consider this 8, 9, 10, Jack, Queen or any king as well. 9, 10, Jack, Queen, King as well will compete for the straight. So what is the probability that the river card competes in the straight, right? So let's quickly head back to collaboratory and check that out. So for our open-ended state case, again, everything here is same, guys. So all we're trying to do is we're changing the outcomes here. Well, in our case, the outcomes, the number of 8s is 4, the number of kings is 4. Well, the number of outcomes that we actually expect is number of 8s plus number of kings, right? And eventually the probability is being calculated by passing outs and eventually the number of sample space. In our case, that's 52. So here, as soon as we go ahead and print it, we'll get the river straight probability to be somewhere around 70%. Well, this means that there is roughly a 17% chance of hitting your straight draw on the river. So now that that's sorted, let's move on, right? So next up, we have mutually exclusive events. So when you're working with multiple events, you might also have events that are mutually exclusive or disjoint, right? When I mean disjoint, they both cannot occur at the same time. Well, in such cases, you might want to calculate the probability of any of the multiple mutually exclusive events occurring. Well, in such cases, you might want to calculate the probability of any of the mutually exclusive events occurring, right? So guys, there is this particular shortcut, right? So whenever someone mentions mutually exclusive, just put this union operation in your head so it makes it quite easier, right? So in such cases, you don't have to multiply the probabilities, but you simply add them and you get the probability. Well, now let's make use of this and we'll actually be determining the probability of the following events, right? So let us check out 2 events. The first event is actually drawing a heart or drawing a club. And the second event is actually drawing an ace, a king, or a queen. So here is a simple program, guys. So we have 4 number of aces, we have 4 kings, we have 4 queens. To actually calculate this, we'll be performing the union operation. As you can see, we have actually added it here. So adding is basically union operation, right? And eventually we're printing it at the last. Same goes for the first drawing of the heart as well. We have 13 hearts and we have 13 clubs. So we're going to be finding probabilities and we'll be eventually adding them. So let me go ahead and run this, guys. So as you guys can check, there is a 50% chance of occurrence of a heart or a club, and there is a 23% chance of drawing an ace, a king, or a queen, right? So now that we've checked this out, next up, we need to check out non-mutually exclusive events. Well, you can imagine that not all the events are mutually exclusive always, right? It doesn't work that way. So drawing a heart or drawing an ace are 2 non-mutually exclusive events. The ace of hearts is both an ace and a heart, correct? So when the events are not mutually exclusive, you must correct for the overlap as well, right? So how do we do this? Let's check it out. And in this case, let's calculate the probability of 2 events, right? 2 non-mutually exclusive events. The first one is drawing a heart or an ace, and the second one is drawing a red card or drawing a face card. Well, let me go ahead and quickly run this. As you can check out in our first case, we have 13 hearts, 4 aces. The ace of hearts is a single card, that's correct. And again, we're performing the union operation, but we're eventually subtracting the number of aces obtained. Because again, that is an ace, right? So if we actually don't subtract this, this is the overlap we were talking about, right? So this is a compulsory operation. So let me go ahead and run this code and we'll have the output. So yeah, as you can see, there is a 30% chance of drawing an heart or an ace, while there is a 61% chance of drawing a red card or drawing a face card as well. And the next concept is pretty much simple as well, guys. So basically independent events. So what is the probability of drawing 2 aces in a row independently? So this independent term, what do we mean by independent, right? So the occurrence of one event will not actually mess with the occurrence of the other event. To tell you that in a really simple way. So consider this, we have our 52 cards. We have outcomes of our aces to be 4. Probability of getting 1 aces is obviously 4 by 52. Probability of getting 2 aces is actually multiplying 2 probabilities together, which we already worked out. So eventually we'll be getting the percentage code out of it as well, guys. So it is 0.6. So now that independent events are clear, let's move on to one of the last concepts, that is the intersection of our dependent events, right? So we checked out independent events, right? So next up, we need to check out something called as dependent events. Well, it's quite exactly the opposite of independent events, right? So by dependent, we literally mean that there is an event which is depending on the occurrence of another event, and then we go forth with that. So here, let us calculate the probability of drawing two dependent aces in a row. So what are the chances of you pulling two aces in a row? So we have 52 cards, we have 4 aces. The first ace probability is calculated, right? And for the second draw, we have to make sure that the cards don't remain 52. We've already pulled out one card, so that makes it 51. So after the second draw, we've actually drawn two cards, right? So it is not 52 and neither is it 51. It actually becomes 50. And the probability is found out by dividing the number of aces by the number of cards remaining, which is 50. So let me go ahead and run this. So as you can check out, it's a value around 0.45 as well. So there is about a 45% chance of probability that you'll be drawing two aces in a row. So next up, I want to cover something called as the expected value. So consider when you're playing the game such as poker, right? You'll be fairly concerned with the questions such as how much money do I make? How much do I lose? On an average, right? So if you repeatedly keep playing this game, is there something that you can use as a pattern or something like that? Well, you can imagine that it is no different for poker, especially when you're a professional poker player, right? So now if the possible outcomes of the games and their associated probabilities can be described by just one random value, then you can answer the above question for yourself, right? So it can be done by computing its expected value. So what is the expected value that we can obtain? It is basically equal to the weighted average of the outcomes. So what do we mean by weighted average of the outcomes? So these outcomes are then calculated by its probability as well. So how do we calculate the expected value? Well, guys, the expected value is basically multiplying the total value into probability. Let me give you a little bit of clarity with an example. So what is the expected values if there is a $100 total value in the pot and your probabilities of the winning the pot is probably, let's say, 0.75, right? So it's pretty much simple. $100 into 0.75 will actually give you the expected value. So it's as simple and straightforward as that, guys. So let me go ahead and run the code for what I actually mentioned verbally. So the pot is at 100 and the probability of you winning is 0.75. So as you can see, all we have done is just a multiplication operation, and you can check out the value is to be 75, right? So the expected value is 75. And here the expected value is really an important concept in poker, right? So next up, we haven't added any opponents at this point. So let's do that. We need to add in an opponent to play against us, and we want to measure what are the odds, right? So let's quickly head back to the presentation to check that out. So guys, let's quickly go back to the first flush example to see how to use expected values to our advantage now. Well, your opponent has decided to be helpful and he has actually shown you his cards. And he has a set of twos, right? Well, to win the hand on the river card, which is the last card, you must hit any diamond except a jack or a two, correct? Well, the jack or two of the diamonds would give your opponent a better hand and a full house and four of a kind respectively as well, guys. So you have to call $20 to stay in the hand, and if you win the hand, you win $60. So if your expected value is greater than $20, you should call the bet, and if it is not, you should fold, correct? So let's figure out if you can actually call the bet, right? So let's quickly go back to Collaboratory and check out the code for that. Well, should we call the bet? Well, we already know that the sample space is 52 cards. We have two whole cards, right? Which is open cards. Opponent has two whole cards, and eventually the community cards, which are opened up four. So it is the total number of cards minus all of the remaining cards in the deck. So now what are the outcomes, right? So we have 13 diamonds and the number of diamonds drawn can be 4. So basically we cannot add those two diamonds eventually, so we'll have to be subtracting them, right? So we have done that in the outs line. Well, we need to find out the win probability as well. So how do we do that? We basically divide it by the total number of cards which remains, guys. Not the total number of cards in the deck, which is 52, but the total number of cards which remains in the deck. And now let's determine the expected value, right? So there is $60 in the pot. So we need to multiply this $60 into the win probability. So basically we're trying to find the expected value here as well. So lastly, we'll be printing the expected value and we'll be taking a decision on that. So the called amount is 20. So if the expected amount is greater than or equal to 20, we'll be calling that round. So if the called amount is less than 20, we'll be folding it as well. So let me go ahead and run this code and see what we get. So here your expected value is only $9.55, which is less than 20. So would you risk it to get that reward? I don't think so, right? So you must fold. So determining expected value is critical, right, to understand at a poker table. And this is actually done mentally by the professional poker players themselves.